Okay, so in this video, I want to derive the Galilean coordinate and velocity transformations. So what you see here are two reference frames or two coordinate systems. Okay, one is S1 and S2. Okay, and S2 is moving with a constant velocity with respect to S1. All right. So S1 has the x-axis is labeled x1, the y-axis is labeled y1, and the z-axis is z1, which is in this case coming out of the page. And similarly for S2 we have x2, y2, and z2, which is coming out of the page. Okay. Now there's an event that occurs in S2, which I'm calling here M. Okay, and what we want to know is what are the coordinates and the time measurements that someone who is in S1 will make for this event. Okay, so what are these? What are the coordinates and the time measurements that someone who is sitting in this reference frame will make for this event here? Okay. We assume in this case that the time that both of these reference frames, okay, so someone who's sitting in this reference frame and someone who's sitting in this reference frame, that the time they measure for this event is the same. Okay, so that's one assumption that we make. So T1 is equal to T2, which we'll just call T. Okay? So how do we go about actually figuring out, okay, what are the coordinates of this event with respect to someone in this system? Okay, so what I've drawn here is actually just the same triangle, okay, here. So this distance here, this vector, O1, O2, this is the distance between the origins of the two coordinate systems. Which I just call D, okay, and this is in the x direction. So this is why there's a I hat there. This is R2, okay, so this is the position vector of this point in S2, and of course we have R1, which is a position vector of this point with respect to S1, okay. So what is R1 and R2? Well, R2 is just x2 I hat plus y2 j hat plus z2 k hat. Okay, the x, y, and the z coordinate in this reference frame. Similarly, R1 is x1 I hat plus y1 j hat and z1 k hat. And as we said, that this vector here, the distance between the origins, I will just call that D. Okay? Now you see here that this vector plus this vector gives me this vector here. Okay? So D I hat plus R2 has to give me R1. Okay? So this is what we have here. So R1 equals to D I hat plus R2. And of course, we know what R1 and R2 are. So we can, for on the left-hand side, we can put in the vector R1. On the right-hand side, okay, we can write this D in terms of the velocity because we know the velocity. Okay, we know that's moving with a constant velocity. So this is going to be the distance divided by the time, as we know, is the velocity. So solving for the distance here, we get that distance is equal to velocity times time. So for the distance here, we can put in the velocity times the time. Okay, and then plus this vector R2, which is x2 I hat plus y2 j hat plus z2 k hat. All right. Now, if we combine the like terms here, okay, the terms with the I hat, we get on the right hand side the following expression that you see here, namely x2 plus vt I hat. Okay? And of course the left hand side here remains the same. Okay? So you see here that this expression on the left hand side has to equal to this expression on the right hand side. And the only way that is possible is if x1 is equal to x2 plus vt, y1 is equal to y2, z1 is equal to z2. And as we said before, we made the assumption here that t1 is equal to t2. Okay, so the time that they measure is the same. All right. So this is what is called, these equations, these four equations are what are called the Galilean transformations. Okay, so these are the Galilean transformations. Call that GT. Similarly, if we solve for x2 here, x2 is equal to x1 minus vt, y2 is equal to y1, z2 is equal to z1, okay, and t2 is equal to t1, okay, and these are the inverse Galilean transformations. Okay, so inverse Galilean transformations. All right, now if we differentiate these equations, we can arrive at the velocity transformations. So if you differentiate, for example, the first equation, which is dx1 over dt, okay, with respect to time, this will give us dx2 over dt plus the derivative of this term with respect to time is just going to be v. Okay, so this gives us that v1x is equal to v2x plus v. Okay, and similarly, if you differentiate the other two equations, what you will find is that v1 y is equal to v2y, and v1z is equal to v2z. Okay, and these are the Galilean velocity transformations. Okay, so we can call this the Galilean velocity transformations. Okay, so yeah, so the inverse will of course just be the we'll just solve for vx2 here, v2x. So v2x is equal to v1x minus v. Okay, 2y is equal to v2x, and v2z is equal to v1z. This should be 1 here. Okay, so these are the Galilean inverse Galilean velocity transformations. Okay.